Hey guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. Before I proceed, I'd like to request our members to kindly go to YouTube and search Ernest Sciences and Mathematics TV channel, subscribe and engage us in the comment section, and also check various description boxes for various links that we put there which are having related content. So in this specific discussion, we're going to look at the concept of Gibbs free energy and Helmholtz free energy. And later on, we are going to develop this one in our second video on the concept of a maximum work function. And of course, this is going to be a more elaboration on the first video that we have done on the concept of free energy and equilibrium. And it's going to shed for us some light on how we are going to represent this particular aspect of the Gibbs free energy and Helmholtz free energy. Now, the Gibbs free energy which we have given an abbreviation as G, and of course the Helmholtz free energy is going to be given as Helmholtz. My pronunciation is correct. So this is going to be represented using capital A, where this one is going to be represented using G as such. So these are the two specific functions, of course, which are going to be used in trying to determine the concept of spontaneity and equilibrium of various transformations. And of course, they're going to be defined in a specific order, whereby we're going to have the Gibbs free energy, which is G, is given as the ratio, or rather the Gibbs free energy, which is given as G, is given as, of course, the value of H minus Ts, whereby we said that H is going to represent enthalpy, whereas the T is absolute temperature, and S is going to represent entropy. And the Helmholtz free energy, A, is going to be given in terms of an algebraic form, which is E minus Ts. And of course, we said that the concept of A is Helmholtz energy is internal energy. This is absolute temperature and the entropy given as such. So later on, we're going to see the relationship that is going to exist between the two. But of essence for us to take note as we proceed is that these specific functions are going to assist us determine spontaneity and equilibrium of various transformations as we're going to go ahead. So therefore, I've mentioned about various thermodynamic variables, which of course include E. And as I said, the E is going to represent internal energy. And then we're going to have S, I said, is going to represent entropy. And then we have T, this is going to be absolute temperature. And of course, we're going to have this particular H, which is going to imply entropy. And this one, of course, as we have given a specific representation, I'm just going to give it in terms of an expression. So we have said that enthalpy H is a state function which can be represented as E, which is internal energy, plus PV, where P is pressure, and then this one is going to represent volume in that specific order. So therefore, these are going to represent the various thermodynamic variables that we're going to employ in our specific discussion. And of course, the concept of Gibbs free energy, which is a G, and of course A, are going to be part of this specific category of the variables that I've mentioned. These are going to constitute, of course, state functions. In various videos, I've talked about state functions, which basically represent functions that are independent of the path, of course, which the chemical reaction or the reaction has taken place. And of course, in that specific case, then therefore, the process is basically going to be independent from the path being taken by this specific change. So having given these ones in terms of equations, so therefore we are going to have equation 1 for Gibbs free energy, equation 2 for Helmholtz free energy, and in particular cases we are going to consider this specific aspect of enthalpy. And of course we are going to also to see other particular definitions we had used, but of course those are going to be the main ones we're going to consider in this specific discussion. Now, if we try to look at the specific changes which are going to occur in this particular representation for these specific functions, especially for the functions which are going to be assisting us in determining spontaneity and equilibrium, we can be able to indicate the representation for a particular function at temperature 1, and of course that is going to be the state of internal energy 1 and entropy S1, or the initial entropy represented at this particular case. So therefore, these are going to be given an equation. So we can be able to give them Helmholtz free energy given as A, which is going to be given in terms of internal energy minus temperature, and then we're going to have entropy given as that. So this is an initial part of a function, whereby we're going to consider these particular variables being represented in this specific order. So after some time, or rather some variable has been changed, for instance, if you move to temperature 2, so therefore we will have the E2 being represented as such and S2 being given as such, and that implies that we're going to have a second state of this specific Helmholtz free energy being given as T2 and S2 respectively. So those are the appreciable changes which we are going to witness being represented as such, and therefore we can be able to give a change in Helmholtz free energy, which is a transition between A1 and A2, by giving it as delta A equivalent to A2 minus A1. And of course, in terms of the various representation that we have given for this, it is going to be E2 minus E1, which is the respective energies being given in that particular case, and the second variables are going to be the product of the two, whereby we're going to have it given as T2 S2 minus T1 S1 respectively. So therefore we're going to represent this specific change from T1 to T2 of the Gibbs, the Helmholtz free energy, using this specific representation, and therefore we can be able to come up with an overall representation for delta A given in terms of a change in energy, which is delta A implying this one, and then we're going to have the second bit being given as delta TS. And in this particular case, then therefore we can be able to consider a state whereby we're going to have a constant temperature, especially for the first change that we had mentioned in our previous discussion. So therefore we're going to see that the temperature is going to change, whereas this specific variable for the entropy is going to be remaining constant. Therefore we can have a general representation for change in Helmholtz free energy given as delta E minus delta or minus S delta or T delta S, whereby T is going to be constant temperature, and therefore we're going to regard this one as an isothermic or isothermal condition or isothermal change in that specific respect. So similarly, we can be able to represent the Gibbs free energy using this specific format. Perhaps I'm going to do it in a quicker way so that it can be more elaborate for us. So for the initial state of our Gibbs free energy, I said we're going to represent the Gibbs free energy using T1, which is going to be H1 minus T1 S1 given as from that general representation. Therefore, the second state is going to be represented as H2 minus T2 S2. So this is going to have a general implication of having a formula of G2 minus G1 is equivalent to H2 minus H1. And of course, this is going to be minus this particular product for the TS. So we're going to have the T2S2 minus T1S1 in that specific order. So generally, then therefore, we can be able to represent this delta G, which is the change in Gibbs energy, using the general representation of a delta H, which is change in enthalpy, and then minus delta Ts given as such. Now for the isothermic change or a constant temperature, then therefore we can be able to give a constant temperature. Of course, we had said that's a situation for example of a phase change. We're going to have this specific delta G, which is a change in Gibbs energy given as a change in enthalpy, and then minus T delta S for an isothermic change in that specific order. So in one of our discussions, we decided that we can be able to fix the concept of pressure, and that specific change is going to be regarded as an isobaric change. So similarly, from the case of consideration whereby we had fixed this aspect of our temperature. We're also going to fix pressure in this specific case. And of course, we're going to have a state whereby we're going to refer to as an isobaric change. So perhaps I'm going to give an illustration for that specific type of a change, or an isobaric change, and we're going to see how we can be able to represent this particular Gibbs free energy in an isobaric change. So we had said that we can represent enthalpy, which is a state function. We had said that this is the same as E plus PV. Therefore, the delta H is going to be given as delta E plus P delta V, given as such. And from the representation of our Gibbs free energy, we had said that this one can be given in terms of course, a delta H, which is a H1 minus H2 as I've given in our previous discussion, or in linear formal discussion from this specific case. Then therefore we're going to do a substitution for this particular section for delta H using this specific representation. So therefore the Gibbs free energy is going to be given as delta E, and then we're going to have this specific part given as plus P delta V, and then minus T delta S given as such. So we can perform a rearrangement of this specific formula, and then we're going to have delta E minus T delta S plus P delta V given as such. And of course, if we try to look at this, we are given the representation of Helmholtz energy using this particular first portion of the representation for Gibbs free energy. So therefore, this particular section is going to represent delta A, and therefore we can be able to develop a relationship between the Gibbs free energy and the Helmholtz free energy in this particular case, which is going to be a general representation of a formula for this, which is delta G is equivalent to delta A, which is an Helmholtz energy plus P delta V given as such. So that's going to give us a relationship for a process which can be described using the Gibbs free energy and the Helmholtz free energy at constant temperature, of course, and pressure. And of course, we're going to see the various applications of this specific formula and trying to represent various energy, especially when we're going to talk about the maximum work function. I've just reserved that second specific discussion because we're going to consider the case of compression and perhaps the case of expansion, and that is going to be more elaborate on how we can be able to describe this concept of free energy and equilibrium. So that is it for now. Catch us in our next video. God bless you. Bye.